I'm going to be talking to you about solving the anomaly equations. I'll explain what the anomaly equations are and how you can use certain techniques to solve them. So some research says that the perfect length for a talk is about 18 minutes long. So what I'm going to do is I'm going to split this talk into two halves, each of which being about 18 minutes. And in the middle, we'll just do something that doesn't require you to think too much. This talk is based on these two papers on the right of the screen, both with Ben Alnak and Ben Koparis at the University of Cambridge. So the first one was published towards the end of last year, and then a more recent one in the middle. In the first half of this talk, I'll explain what the anomaly equations are, where they come from, and then we'll look at the pure U1 case. So that's taking a pure U1 gauge theory and looking at how to solve the anomaly equations for this case. And then in this little brain break, I'll tell you about the history of some of the more historic characters that come into this talk. In the second half, we will look at extending the standard model. So that's adding an extra U1 to the standard model gauge group. This could be, for example, corresponding to a C prime boson, so an extra U1 force. I'll then tell you why you should care, why you should be interested in this solution, and then conclude. Okay. But before I start, let me tell you a little story. And this is a story to just motivate some of the ideas behind what we're doing. So the way the undergraduate system works here in the UK is that you have to choose a very specific subject. So you either choose something like physics or maths. Now, as a high school student, I was debating of whether do I do physics or maths. So maths is something very pure and intrinsic about it. Whereas physics is relevant to experiments. You measure the real world and you say something about the real experiments. I ended up going down the physics route, but I've always had this interest in the mathematical side, in the pure mathematical side. And what I've been doing in my PhD is taking this pure mathematics side and applying it to problems which are relevant to experiments, relevant to physics that you may possibly measure at experiments. And what I'm going to show you in this talk is probably the prime example of this. We're going to start with a gauge theory, and then we're going to turn that into a problem in number theory, and then use techniques which are fairly well established in number theory to solve that problem. Okay, so let me start by telling you what an anomaly is. When I say an anomaly, I mean an anomaly when it comes to the symmetries, rather than an anomaly, for example, like the B anomalies. So for these types of anomalies, you have a symmetry, and that symmetry can act on certain things. For example, it can act on your classical theory. So it can act on your action or your Lagrangian, and that action and Lagrangian can be invariant under your symmetry group. It can also act on the quantum theory, but your quantum theory contains slightly more information than your classical theory. Instead, as well as just having the action and the Lagrangian, it also contains the path integral measure. And what an anomaly is when your symmetry is the symmetry of the classical theory, so your action is invariant under the symmetry, but isn't a symmetry of the quantum theory. And this occurs when that path integral measure isn't invariant under the action of your symmetry group. So when your path integral measure shifts by the symmetry group. For something like a global symmetry, anomalies are completely fine. They're okay. They basically mean that if you walk into your classical laboratory with your springs and pendulums and you do an experiment there, that symmetry is obeyed. But then when you leave your classical lab and walk down the corridor into your quantum lab, where you have, for example, lasers or a particle accelerator, then that symmetry is no longer obeyed. There's nothing intrinsically wrong with this. It's just a bit weird. For gauge symmetry, however, anomalies are not okay, because for a gauge symmetry, you need the gauge symmetry in the quantum theory to prove its renormalizability and its unitarity. And if you don't have your gauge symmetry, you can't prove that. And even at a more intrinsic level, when you write down a gauge theory, the gauge symmetry comes as a choice in a section of a principal bundle. So you're kind of fairly inconsistent if it's not also a symmetry at the quantum level. So when we have a gauge symmetry, we need to make sure that our theory is free of anomalies. Let me take the simplest example. a theory with 3 left-handed file fermions. So this is going to be the particle content of our simple toy theory. And by the way, throughout this talk, I'm going to take everything to be left-handed. So there will be a time when we go onto the standard model. And when we get to that, some of the representations might be slightly different to what you're used to. And that's because I've made everything left-handed. Okay, so back to this. We have 3 left-handed file fermions, and we're going to assume we have a U1 gauge symmetry. This U1 is going to be a U1 group gauge symmetry, so each of our fermions lies in a representation of that group. And those representations are labeled by an integer charge x1, x2, and x3. Now, I'm going to re-stress this, that these are integers. This is because you need 1 to map to the same thing as e to the I2 pi under your gauge symmetry. Sorry, under your representation. And if these weren't integers, that would not be the case. Okay, so this is our theory. And we're going to write down a Lagrangian, a classical Lagrangian, which is invariant under this gauge symmetry. And we take that action, or the Lagrangian, and we stick it into the quantum theory. And then we ask, what do we need to be satisfied for the theory to be absent of anomalies? And it turns out that we get a set of equations. These equations down here. So we get x1 plus x2 plus x3 equals 0, and x1 cubed plus x2 cubed plus x3 cubed equals 0. So if these equations hold, then our theory is free of these anomalies. I'm actually specifically talking about local anomalies here. There's another type of anomalies called global anomalies, but let's not worry about those. So in this talk, every time I say anomalies, I'm going to be specifically talking about local anomalies. So these are a set of equations. I haven't just pulled them out of nowhere. You can either get them from index theorems in topology, which I'm sure none of you really want me to go into on a Friday, or from triangle diagrams. So the index theorems in topology gives you these equations exactly, whilst the triangle diagrams, it's a perturbative method that it gives you the right answer. So in these triangle diagrams, you have the 3 far fermions running around this triangle, and on the vertices, you have the gauge bosons. So you can have, for the first diagram, 2 of the gauge bosons are gravitons, and 1 of them is the gauge boson corresponding to our U1 gauge symmetry. And for the second equation, for the cubic equation, all 3 of those gauge bosons are the gauge boson corresponding to the U1. And you can, and certain conditions of these diagrams have to be satisfied, and you can show those conditions are equivalent to those equations being satisfied. So let's take a look at these equations. These are polynomial equations in the integers, okay? And these have a very specific name in number theory. These are called Diophantine equations. Now, before I started working on this area, there was another group in Cambridge that was also looking at these anomalies or these types of equations. And we had these meetings, and they were using the phrase Diophantine equations. And I never had looked what it meant, and I thought it was this complicated type of equation. But no, Diophantine equations just means polynomial equations in the integers. So if I use Diophantine equations in the rest of this talk, just think it means polynomial equations in the integers. I'll try not to. Okay, so let's take a look at these equations. Now I want you to try and think about how you would try and solve them. So this last equation, this cubic, may look familiar. It takes the form of Fermat's equation and can be solved using Fermat's last theorem. So Fermat's last theorem tells us that one of those charges has to be 0. In other words, the only solution to this is if one of these charges, x3 for example, is 0, and the other 2 are the negative of each other. So x1 equals minus x2. And if you substitute those into the first equation, you can show that they are satisfied. Right, but we started with physics. We started with a gauge theory, and we took and we set the condition that our theory had to be free of anomalies. then we got these equations, which were polynomial equations in the integers of what's called Diophantine equations. And then we showed using Fermat's last theorem that one of the charges had to be 0. So we used Fermat's last theorem to tell us that if we have a gauge theory with 3 left-handed far fermions, one of them, and a U1 gauge force, then one of those particles has to have no charge. It has to be in the trivial representation of that gauge group. And this is what I meant at the start of this talk. This connection between taking something formal in mathematics, number theory, and applying it to something in physics, gauge symmetries, and the allowed representations of gauge symmetries of gauge theories. So how do we generalize this? The first generalization you can account for is to take not 3 left-handed far fermions, but n left-handed far fermions. And these could be, for example, a dark sector where you only have a U1, which is charged, where only your dark particles are charged under a gauge U1. So we give each of these particles a charge x1 through to xn, and we look at those triangle diagrams again, and we ask, what are the conditions for this theory to be free of anomalies? And we get pretty much the same conditions, just generalized. Instead of summing over 3, we go to n. Basically, those triangles we had before, instead of 3 far fermions running around the triangle, you have n. Now, these equations were first solved in this Costa-Duboscu and Fox paper, and apologies if I pronounced any of the names wrong. And so they gave the solution to this equation. And then what Mealer-2-Benz did was gave a geometric interpretation of their solution. I'm going to explain our geometric interpretation just because it's what generalizes to the standard model case, what I'm going to look at in the second half of this talk. But if you actually want to see the solution itself, I would recommend looking at their paper. And they also have a series of follow-up papers looking at where you have more than one U1 gauge force. So how do we solve these equations? We know that we have some solutions, right? I can tell you some solutions. Set x1 equal to minus x2, and all of the other charges equal to 0. That is a solution to these equations. And here's a little secret from number theory. One solution is many. The reason Fermat's last theorem was so difficult to prove is that you were trying to show if there were solutions or not. So in number theory, proving the existence of a solution is incredibly difficult. But if you have some solutions, it's very easy to find more. And if you find enough solutions, it's quite easy to find them all. And this is the basic principle behind how you solve these equations. Okay, so let's take a look at how you solve these equations. I've written the equations down here, but I don't really want you to think too much about the equations and about the process. It's more about the geometric interpretation of the method that I want to focus on in this talk. But let's start with the linear equation. How do we solve the linear equation? I mean, that's easy. You just rearrange it. You set xn equal to the minus of the other charges. So we then take that, excuse me, we then take that and we substitute it into the cubic equation. And we get this equation, which is in terms of n minus 1 charges. Now, I want you to imagine the whole screen is the space represented by those n minus 1 charges. In other words, the parameter space of those n minus 1 charges. We know there are some solutions to this, as I mentioned. You can set x1 equal to x minus x2, x3 equal to minus x4, and so on, and so forth. And these give you actually 2 planes of solutions, one corresponding to that, and then the other one corresponding to x2 equal to minus x3, and so on and so forth. So we have these 2 planes of solutions. If you don't understand where they come from, just take it as given that we have these 2 planes of solutions. I'll give you an expression from them later. And we're going to take 2 points, the point A and the point B, on these 2 planes, which we know. And we're going to draw a line between them, this orange line here. And if we take the left-hand side of this cubic equation and we project it down onto that line, so we consider its value along that line, we're going to get something like this. So we know this cubic has to pass through 0 at the point A and the point B. But because it's a cubic, in other words, it has to take the shape on the screen, it also has to pass that line at another point P. And because we know A and B, the point P is really easy to find. It's basically a linear equation. So we have gained a new solution. Given the points A and the B and the point B, we have found a new solution P. And this is what I was talking to you about. This is what I was mentioned, that if you know some solutions in number theory, it's very easy to find others. So all you really need is these two planes to be big enough that every point in your ambient space or your space of charges lies on such a line. And if that's the case, which it is for us, then you simply scan through these lines, lines from points in this plane to points in this plane, and you pick up all of the solutions. That's essentially the method of the solution. That is essentially the geometric interpretation, or that essentially is the solution. I'm going to flash the solution up on the screen, but like I said, if you actually want to see the solution, I would recommend not looking at our paper, but the Koster-Dabrowski and Fox paper, just because they give it in a much nicer form than what we do. So like I said, at the start, the perfect length for a talk is about 18 minutes. So I'm going to take a quick timeout so you don't need to stop. You can stop thinking about everything I've been saying. And here's some random facts which are not relevant to the rest of this talk. And it's about some of the history of the characters involved. The first character is Diophantus of Alexandria, and not much is known about him. We know he lived around 201 AD. And what we do know comes in a series of problems or poems by this Greek philosopher or mathematician, Methodius. And this poem here, and because it's a poem, I'm not going to attempt to read it out, gives you how old Diophantus was when he died. So if you have some free time, maybe tonight or over the weekend, you can try and work out how old Diophantus died from that problem or poem. The second character is Pierre de Fermat, and everyone knows his quote, which he wrote in the margin. It's impossible to separate a cube into two cubes, or a fourth power into two fourth powers, or in general, any higher power than the second into two like powers. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. The interesting connection between Fermat and Diophantus is that Fermat wrote this in one of Diophantus's books. So he wrote this in Diophantus's Arithmetica. And Diophantus wrote a series of books, many of which were lost, but some of them were preserved. And Fermat wrote this quote in this book. The last character, who hasn't appeared explicitly, but many of the concepts come from him, is this character called Mordell. So he was an American-born British, and he studied here in Cambridge. And like I said, he wrote a book on Diophantine equations. And many of the concepts he used in this book are the concepts that we've generalized to solve the equations in this talk. So he gave a method to solve cubic equations with three variables using lines and planes, and we generalize that. Okay, so let's put our thinking caps back on, and let's look at extending the standard model algebra. We all know what the standard model is. We have an SU2 plus SU3 plus U1 gauge algebra. And we have 5 species of particles. And these are our representations with respect to that algebra. And what I'm going to do is add a right-handed neutrino. Now, I can give you a phenomenological reason for me adding a right-handed neutrino. It helps give the neutrino's mass. But that's not the true reason we added it. The reason we added it is because we couldn't solve the equations in this case. I'm going to give you the analytic solution to the anomaly equations for this problem. And our solution is going to rely on the point corresponding to baryon number minus lepton number, which doesn't exist in this case, but does exist in this case. And this is a fairly interesting fact, that you can only really solve these equations, or we only know how to solve these equations if you add right-handed neutrinos. I've also been naughty in one other respect, and that's that I've only written one family down. The standard model has 3. So when we add an extra U1 to our theory, like this, and we give each of the particles a charge with respect to that U1, I'm not necessarily going to assume family universality. So I'm not going to assume that, for example, the quarks have the same charge in that extra U1. Now, again, I can give you a phenomenological reason for this. To explain stuff like the B anomalies, you need family non-universality, and this is one way which you can get it. Here's a more mathematical reason. There is no reason a priori to assume family universality. You could argue that you have family universality because the hypercharge is family universal, but the hypercharge is only family universal after the fact you've added the hypercharge. Before you've added the hypercharge, the U's and the D's are the same family, and therefore they're the same representation, and it's only after they separate into two distinct families. Counter-argument to this is that you could have an extra gauge force mix in the three families, and then you would require family universality. But if you didn't understand any of that, for generality, we are going to assume that our families can have different charges with respect to this extra U1. And this extra U1 can be related to, for example, an extra C prime boson, or it can be related to a larger gauge extension, or it could be a sub-algebra of a larger gauge extension. I'm going to write down the anomaly equations for this, and these come from exactly the same place they came from in the U1 case, those triangle diagrams, or, if you want to get technical, those index theorems in topology. So this first one comes from the case when you have two gluons, and then one C prime boson going in to your triangle, and so on and so forth. I should have mentioned, I forgot, sorry, these QJ, these charges are all going to be integers because we're going to assume our gauge group is compact. So Q1, Q2, Q3, and so on and so forth, they're going to be integer charges. So these equations are a set of Diophantine equations in the integers. I'm not going to tell you, I don't want you to actually focus too much on the equations, because the method I'm going to give you is fairly simple without having to worry about the details of the equations, which are for me to focus on. But let's think about what's the first thing we would do if we were presented with these equations. Well, one thing we could do is simply scan through all possible sets of charges. So scan through every Qj, Uj, and Dj, and Lj, and so on, from -10 to +10, and then just see which are solutions. So this is exactly what Ben Alanak, Jody Figi, and Scott Malther did almost 2 years ago. They scanned through those sets of charges from -10 to +10. So that's about 1.5 times 10 to the 19 sets of charges, and they scanned through them in a clever way, which meant they didn't actually have to scan through them all. And out of those charges, they found 21 million of them to be solutions. To put those two big numbers into perspective, if every grain of sand on this beach was a set of charges, then about one of them would be a solution. So that's how sparse these solutions are compared to the charges in general. So one thing I haven't told you so far is why you should care, why you should be interested in what I'm talking about, why you should be listening to what I'm saying. Here's the thing. I don't know why you should care, because I don't know what you will work on, and I don't know if you're watching this and you're thinking, I could use this to do this, or I could use this to do this. Or you could be watching this and saying, solving these equations is completely pointless. I can't tell you why you should care, but what I can tell you is why I care, why I spent a year of my PhD working on these equations. The first reason I care is that we have a reduction in parameter space. By solving these equations, so I'm going to give you an analytic solution to these equations. By solving them, we have taken the parameter space of all possible C prime models, and we've reduced it to a parameter space of phenomenologically significant or phenomenologically relevant C prime models, ones that could be seen at experiments, for example. The second reason is you can randomly sample solution space. I'm going to give you at the end a parameterization of the solution. We have a mathematical script for that solution, which you can put the parameters in, and it will output a solution. And if you randomly put, or when I say output a solution, I mean output a set of charges which satisfy the anomaly equations. And if you randomly choose parameters, you will randomly generate solutions. Now, those two are very much to do with the solution itself. But there's more to this than just the solution. There are special structures involved in the method to get there. So in the first half of this talk, we use those two planes to find solutions. Those two planes don't always exist. They exist in special cases. In the next slide, when I give the analytic solution to the anomaly equations for the standard model, we're going to use the point corresponding to baryon number minus lepton number. And that's incredibly special when it comes to these anomaly equations. And it's not just for these equations, these special structures are useful. We're in the process of writing a paper which uses these special structures to tell you a lot more about the gauge theories themselves, or about the structure or the allowed structures of the gauge theories. And the more intrinsic note is we have an understanding of the geometric and number theoretic method of the solution. Now, the solution I'm going to give you at the end is not nice, I'll admit that. But the method we use to get there is pretty beautiful and elegant, to be honest. In the paper, we had a quote that said, "This paper uses mathematics no more complicated than was once taught in kindergarten." That is not explicitly true, and we were told to remove it by one of the referees. But in the next slide, I'm literally going to show you two lines crossing, and that is going to be the solution to these equations. So let me show you. This is the solution, the thing in the middle of the screen. I've written out the equations we're trying to solve, the charges we're trying to find on the left-hand side. I've just written them there to tell you we have linear equations, we have a quadratic, and we have a cubic, but just ignore their explicit form. They're for me to deal with on dark days when I have nothing better to do. So here is the solution. I'm going to go through this twice, once quickly, and then I'll go through it step by step slower. So the first thing we do is we restrict to the subspace satisfied by the linear equations. And that was very similar to what we did in the first talk. We then take a known solution to the quadratic, this point C, and an arbitrary point S. And this arbitrary point S is going to form the parameters of our solution. And we draw the line from C to S, and we project the quadratic down onto that line. And because it's quadratic, it crosses that line at C, but also at one other point, R, this point here. We then draw the line from R to the point B minus L, baryon number minus lepton number. And as I've said, baryon number minus lepton number is very special when it comes to these equations. It's the only point which is a double point of the quadratic and the cubic. That means that this whole line lies in the quadratic and it crosses the cubic at exactly one more point, that point X. Now X is both on this line, so satisfies the quadratic, and satisfies the cubic, and it's in the space PL. So it's a new solution to our anomaly equations, or in other words, these equations here. It's a new permissible set of charges your C prime model can have. Now that was probably a bit fast, so let me go through this step by step a bit slower. Let's take everything away and add them in slowly. The first thing we do is we restrict to the subspace satisfied by the linear equations. Now that's exactly what we did in the first half. We basically just rearranged the linear equations and we find the subset of charges which satisfy them. We then find the point C. Now the point C is any known solution to the quadratic that also satisfies, that's also in the space PL, also satisfies the linear equations. What we did is we just looked at the numerical scan Ben, Joe, and Scott did, what I showed you a few slides ago, and we just took one that looked nice. We then take a point S. That's any point in this space PL, and it's going to form the parameters of our solution. So we're going to scan through all possible S. And we're going to draw the line, this greenish line, from C to S. If we project the quadratic down onto that line, we get something like this. And because it's quadratic, it must cross that line at C, but also at another point R. So R is a new solution to the quadratic. Let's call it that. We're then going to take the point baryon number minus lepton number and draw the line from B to R, this orange line here. Now, because B, or B minus R, is a double point of the quadratic, if we project the quadratic down onto this line, we get something like this. B has to be at the minimum of that quadratic. The double point bit basically means it's a point of multiplicity 2. But this diagram looks wrong, right? Because I've already told you the point R lies on the quadratic. But the only way this can occur is if this line, if the quadratic is actually in this line. So every point on this line has to be in the quadratic. But B is special in another sense, because it's also a double point of the cubic, which basically means it's at an extrema of the cubic, or in other words, at a maximum or a minimum. The cubic therefore looks something like this. And it has to cross this line at exactly one further point, x. Now, x is on the cubic and on the quadratic, it's on the cubic and on this quadratic, this dotted line here, and it's also in the space PL. So therefore, x is a new solution to our anomaly equations. And you can show just by setting s equal to x or s equal to s solution that you can find every solution in this way. Okay, that is the solution, or the geometric method behind the solution, and the thing that gives you the solution, or the interpretation of the solution. This is the solution written out explicitly. Of course, I'm not going to spend long telling you about this. The q and the c are just functions. This is the point R in my previous slide, and this is our new solution x. The delta functions take account of certain special cases I'm not going to talk about. Okay, so that's basically my talk. So let me quickly conclude. And the thing I want to emphasize in this conclusion is where we started from. Remember, we started with this very simple example where we had 3 left-handed bar fermions, and we enforced the conditions of anomaly cancellation. And from those conditions, we got a set of Diophantine equations or polynomial equations in integers. And we used Fermat's last theorem to constrain those charges, to tell us that one of those particles, one of those left-handed bar fermions, had to be in the trivial representation of the gauge group. And then what I've been doing throughout the talk is taking this idea and applying it to more complicated situations. And sometimes I realize this gets lost in, maybe this got lost in what I was talking about, but the thing you have to remember is the solution I have given you is constrained on the allowed charges, on the allowed representations these particles can have under a set time gauge theory. And there's also the number theoretic and geometric solutions behind it, the methods, and also the special structures. So that concludes my talk.